John Connor, and if you're listening to this, you are the resistance. Oh wait, wrong video. Hi, this is Mr. Zarzak, and in this screencast, I'll be talking about electric fields. Let's get into it. Okay, first things first, what's an electric field? Well, it says right here, an electric field is defined as the force experienced by a small positive test charge. Memorize this definition, please. It's going to take a while for you to understand it, so it's better to just memorize it first. When it comes to charge, there's two varieties. There's positive and negative. So we define the electric field in terms of the positive charge, knowing that positive and negative charges have exact opposite behaviors. In fact, that's why they're named that way. So if we can understand the behavior of a positive charge, then we can understand that the behavior of the negative charge will be exactly the opposite. Now, what about the field part? Okay, well, a field is just a space. And in fact, we're all in a field right now. We're in a gravitational field here near Earth's surface. Everywhere we go, we feel this effect of gravitation. It's a force that acts on all objects that have mass. Well, an electric field is just a force that acts on all objects that possess the quality of charge. So what I have here is just an example of some positive charge. And what I'm going to do is imagine a small positive test charge. So I'm just going to draw this in. Okay, and this little positive test charge has to be small compared to the thing I'm trying to test the field around. So if I put my little positive charge to the left here, it's just going to get repelled away to the left. If I instead moved it over here to the right, it would be repelled away to the right. If I moved it below, it would be repelled away to down. If I moved it above, it would get pushed up and away. If I put it over here, it would get pushed up and to the right. If I put it over here, down and to the left, and I can continue this process. The point is that anywhere I put it, it's going to be repelled away. So I can use this idea to conclude that the electric field around a positive charge radiates outward like this in all directions. Anywhere I put the positive charge, it would be repelled away, so my electric field looks like this. And it's just a map that shows me what the force would look like experienced by some small positive test charge. Now, if you remember from Coulomb's law, the electrostatic force depends upon how much charge is interacting, and it also depends on how close charge is to any other charge. And so I'm just going to draw a little ring real close here, and you see that when I'm close to my positive charge, okay, that the lines are spaced together very closely. If I take and I draw another circle a little farther out, you see that the space that I have between one field line to the next is spread out a little bit more. The point is that the diagram is intuitive in the sense that the electric field gets weaker as you get farther from the source, in this case being this positive charge. And so how dense the field lines are, this field line density, gives us an indication of how strong the field is. And that just means that the more bunched up the lines are, the stronger the field. Likewise, from Coulomb's law, the amount of charge present will also increase the electric force and hence the electric field. So I've got a little bigger positive charge here drawn just as a representation of more positive charge collected. How I collect the charge is not as important right now, but if this positive charge is twice as much as on the previous slide, well, then to show that, I would just draw more field lines. So on the previous slide, my electric field looked like this, okay, to show that this is a stronger positive charge and hence a stronger positive electric field, I just draw more electric field lines. Okay, and you can see that as I draw more lines, okay, well then the lines are more bunched up, whether I'm close. You see that field line density is very high. The lines are very close together. And as I move farther away, okay, the field lines get less dense, so the electric field gets weaker, but here the number of lines, the density of the lines is still greater to show that the electric field is stronger around this positive charge no matter what the distance is compared to less positive charge. Now I'm just going to repeat the process for a little negative charge here. So I'll just draw in a little positive charge here. And because we know that opposites attract, this little positive charge would just get pulled to the right, attracted to the little negative charge. Likewise, if I just took my little positive charge and moved it over here, it would get attracted to the left. And if I moved it up here, it would get pulled downward. If I moved it
over here, it would get pulled down and to the right. If I moved it over here, it would get pulled upwards. Basically, anywhere I put it, it's going to be attracted to the little negative charge. So, clearing all that out, I can just imagine the electric field to look like this. Anywhere around this negative charge, the little positive charge would be attracted. And so we say that the electric field around a negative charge points radially inward. Just like with the positive charge, the closer I am to the source, or the closer I am to that negative charge, the more bunched up the field lines get, so the stronger the electric field. Also, just like the positive charge, if I have a larger grouping of negative charge, well, then I show that with more field lines. And so instead of just drawing those 8 lines that I had before, if we say that this charge is twice as big as the -4, I would just add in twice as many lines. Okay, and it gets a little bunched up, but we can see that the arrows are all pointing towards the negative charge. Okay, and we look something like this. Okay, now let's look at a positive charge and a negative charge. We're going to assume that for this diagram, the magnitude of the positive charge and the negative charge is exactly the same. All right, so the first area I'm going to focus on is the space directly in between the two. Not above or below, we'll get to that in a little bit, but right in between. Anywhere in between, there's going to be a repulsive force from the positive charge and an attractive force from the negative. Remember, the electric field is defined as the force experienced by some small positive test charge. And so what we wind up with is that the electric field right in between goes right from the positive over to the negative. Now, what's kind of interesting about this is that the size of the electric field is the same. It's uniform all the way along from the positive charge to the negative charge. The reason that this is so is that if I imagined a small positive test charge right in between the two, there would be a repulsive force from the positive and an attractive force from the negative. If I summed up those two vectors by putting them tip to tail, they would result in an overall force that would go something like this, twice as big as each of the individual components. Now, if I instead imagined my little positive test charge somewhere over here, closer to the positive charge, okay, well here, the repulsive force from the big positive charge is going to outpush the attraction from the negative. So in other words, I have a big force and a small force, but when I add those two forces up together, the sum of those two vectors is actually going to give me the exact same size resultant as it was when the little positive charge was right in the middle. I could do the same thing if I put my little positive test charge over here. If I was closer to the negative charge, well, then I would get this big attractive force from the negative charge. I'd get a smaller repulsive force from the positive charge because now it's farther from the positive and closer to the negative. And the result of that would be a resultant force that would be the exact same size as everywhere else in between the two charges. The next area that I'm going to look at is directly to the left of the positive charge. Over here, there's going to be a repulsive force from the positive charge. There's going to be an attractive force from the negative charge. But because in this region over here, we're closer to the positive charge, the net force, and hence the direction of the electric field, is going to be away from the positive charge. So the electric field would go off like this. All right. And I want to fill this in just a little bit more so that you see that it starts at the positive charge. Okay, so anyways, now I'm going to look over here to the right of the negative charge. Over here, there's going to be attraction to the negative charge, and there's going to be repulsion from the positive charge, but because our little test charge will be closer to the negative, the attractive force is always going to win out, and so the electric field is going to point inward like this. All right. The next area that I'm going to look at, all right, is going to be up above the little positive charge over here. So imagine if my little positive charge started right here. Okay, if it was just this positive charge, it would get pushed away like this up and to the right. Okay, but rather than just get pushed up and to the right, it's also going to get attracted towards the negative charge. And so the result of this is that it's actually going to wind up making kind of an arc going from the positive to the negative. Okay, and again, if it was just the positive charge, it would go off like this, but because the negative charge would attract it, it winds up curving. Now this is symmetrical, which just means that down here we'd have a curve that looks something like this. All right. And if I kind of repeat this process, okay, it's symmetrical about both, so it takes on this shape that looks like this. All right, the last little area that I want to look at is this region over here in the corner. So there's 4 corners, okay, but if I can kind of get the shape of what's going on in one corner, okay, I know what's going on with all of them. So if I look just up and to the left of the positive charge, if it was just the positive charge, it would just get repelled away in a straight line just like this. Okay, but there's also this attractive force that's going to happen always kind of towards the negative, so it's going to get pulled that way. And so what's going to happen is the electric field's going to get skewed a little bit. And so what's going to happen is that the direction of this, so let me do this in red, the direction of this is going to wind up kind of curving like this. And in fact, what's really going on here, okay, is this is just making an even bigger field that would come in over here. So the truth is that this electric field curves around and comes in like this. And again, this is symmetrical, okay? So this would like go off this way and it would come in over here. And I could draw on more of these if I need to, but we've got the shape of the curve now. We got what's important, so it kind of goes off like this, and it comes in over here. It goes off like this, and it comes in over here. Okay, and I could fill in more of these if I wanted to, just to show all the space filling in. Okay, and that's getting pretty messy, so I don't think I'm going to do any more. I think that's enough for you to see the point. All right, so with that, we now have enough drawings to really summarize the big points about electric field lines. Okay, so electric field lines are always going to start on positive charges. And if there's no positive charges present, they're going to come in off the page. Well, really, those lines can stretch out to infinity. Okay, in the sense that they always start at some positive charge somewhere, whether they have to permeate all the space or just keep going until they find some positive charge to start on. And the same is true with negative charges. Okay, those electric field lines are going to end on negative charges, and if there's none present, we'll just show them going off into infinity, because they're always going to end at some negative charge, so those lines would go on forever until they find someplace to terminate. Point number 2, electric fields do not cross. Okay, so we never crisscross, because then that would show the force being in 2 different directions simultaneously, and which doesn't make any sense. There's always got to be a net force in some direction. And the other big property is that more field lines is an indicator of a stronger electric field. Okay, next we're going to look at the electric field around 2 positive charges. And for simplicity, we're just going to assume that these 2 positive charges are equal in magnitude. I'll remind you one more time that the electric field is defined as the force experienced by some small positive test charge in the presence of an electric field. All right, now, rather than go through area by area and try to map this out, I'm going to give you another way to think about this that's going to let us get our picture a little bit quicker and hopefully help you understand this electric field idea a little bit better. All right, so let's pretend for a second that the positive charge on the left was all by itself, that positive charge on the right wasn't there. Okay, well then we know what the electric field is going to look like. It would just radiate outwards in all directions, because anywhere near this, all right, a positive charge would be repelled away. All right, I drew that kind of sloppy. My arrows really should start on that positive charge, but I'm going to erase them anyway. Because to get the combined picture for both of them, I'm going to remember that with 2 positive charges would repel one another. And so what's going to happen is that the electric field lines are actually going to repel each other too, almost as an analog to the repulsiveness of the 2 positive charges from each other. So what I mean by that, okay, is if I start an electric field line, okay, let's say this would start going off like this, but what's going to happen is that electric field is going to get curved because it's going to be repelled away from this positive charge over here. And the same thing is going to happen on this side. This should just be going up and to the left, but it winds up curving away like this because this electric field is being repelled away, or more importantly, I guess, this charge is being repelled away by this one. And that's kind of the key, okay? I'm going to start all these lines off going the way that they would go just kind of if it was just one positive charge. But then I'm going to curve those lines away to show that the fields are literally repelling one another. And if I just kind of repeat this process, okay, one over here, and then one over here. Okay, and this is really all I need to do to map out the electric field. I'm just going to continue this process. And so like the direction of the curvature for both is exactly the same. the arc of the curve is the same regardless. So like this. And in the space directly to the left of this positive charge or to the right of this positive charge, well, then the electric field will just go straight away because both charges would repel away some small positive test charge. Now, the point of confusion with all this is always what's going on right here in the middle, okay? There's some infinitesimal to where if I could get some positive charge exactly here in the middle, okay, I could get to equilibrium, but you're never really going to get there. So you just have to use a little bit of imagination in that the electric field lines just kind of fill in this space smaller and smaller and smaller until you eventually you get, if I remember my math right, there's a little space and it's called asymptote, okay, in here. But the point is that the electric field will fill all this space right down to some little infinitesimal there in the middle. So that's plenty to get a picture of what's going on here. I'm actually going to erase a couple of these because a few of these look like they're crossing, and I don't want to break one of the rules. Okay, with this picture, I think it's kind of clearer if you just sort of focus in on, say, this one over here. Okay, it's almost like there's some force pushing all these field lines to the left, and if I look over here, it's almost like there's some force pushing all these field lines to the right. And that's the idea. This is electrostatic repulsion, so the field lines are repulsed from one another just like the charges are. To help you visualize all this, we found this really great online simulation. So I'd pause the video now and go open this up in a web browser. We've also linked this for you in the review materials folder for this unit. So here's what the page looks like. Okay, I'm just going to scroll right down to the simulator here. And we've got these two slider bars that we can control. The red is positive charge and the blue is negative charge, and I can actually see that just by looking at the directions of the arrows. So in other words, where those field lines start and where they terminate. I can set these to whatever I want. Okay, so go ahead and play around here with a little bit with this. So I've got charge number 2 set to nothing at all, so I can just crank charge number 1 up. The higher, more positive I make it, the more lines I see. If I make it negative, same trend, just opposite direction. Okay, so it's just, I'm going to make this one up to 5. Okay, and then if I take this down to -5, there's that more complicated, more lines, but still just the same basic shape that we matched out before. If I make charge number 2 less magnitude, but I keep it negative, okay, you'll see that charge 1 starts to take over and have a bigger influence on that charge, almost like it's dominating the field. And if you're close to the little red positive charge, it's almost like you can't even see that those lines are bent at all or skewed at all because the field is so much stronger coming from the positive charges compared to the negative. I can also crank this up, okay, and look at what 2 positive charges are that are really strong. Okay, so anyways, I can do any kind of combination I want with this. So the point is that you need to play around with this a little bit and get used to what these pictures look like, because you'll be responsible for doing some of these drawings on the test, okay? So I made a few drawings just so you can see, one, that the larger the magnitude of the charge, the more field lines that we have, and 2, so you can see how the electric field gets skewed depending upon the relative magnitudes of the charge. So you want to study these, and if you have any questions, contact your instructor. I just put in a bunch of arrows. Oops. So just to put some numbers to this, I put together a little sample problem where we have a little -1 microcoulomb charge here on the left, and our job is to figure out what's the magnitude of the charge on the right. So to do this, all I got to do is count. Okay, so if I start on this side, I count 1, 2, 3, 4, 5, 6, 7, 8 field lines. Okay, so now I'm going to go to the other side. I'm going to start right here and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I see twice as many lines on this charge on the right as on the left, and so that tells me that this charge on the right has a value of -2 microcoulombs. And just to make these diagrams accurate, all these lines need to terminate on negative, so I'm just going to draw little arrows pointing towards the negative charges, just so that my picture is accurate. Okay, so just go through and do those. And definitely a little bit bunched up over here, but we just want to show that those field lines and on the negative charge. So then one more quick example, given this 20 microcoulomb charge here on the left, determine the charge on the right and also determine the direction of the electric field lines. So go ahead and pause the video because in just a second I'm going to reveal it, see if you can answer the question, and then when you think you have an answer, just unpause it. Okay, and the solution is 5 microcoulombs. And here's the direction of the arrows for these electric field lines. Hopefully you got it. If not, give it a little thought, see if you can work it out. And if you're still stuck, contact your instructor. This is Mr. Zarzek saying thanks for watching this tutorial on electric field lines. See you next time.